So I'm going to go through this transport and membrane workshop to provide you some insight as to some possible answers. To begin with, this first one uses chloride ion versus this indole ring as a kind of trying to figure out what happens when you go from one side of a membrane to another. So I'm going to go ahead and just draw that real quick. So let's say these are the two layers of the membrane that I just drew here. In both cases, when we're in one side of the membrane, these species that you see here, the chloride ion and the indole, are going to be surrounded by water molecules. In the case of the chloride ion, it will be very favorable. The water molecules will like to be part of this chloride ion. It's going to have a sphere of hydration wrapped around. In the case of indole, not going to be nearly as comfortable with the water because this is largely nonpolar with a little bit of polarity at that nitrogen NH group. But overall, it would be fairly nonpolar. So there would be water around it. But to remove those waters would be much easier than to remove the chloride ions that you see here. The water around the chloride ion, because ion dipole interactions are holding the water with the chloride ion, whereas induced dipole interactions are dealing with the water. So in the interior of this membrane, there are lots of fatty acids that are coming down. So the interior of a membrane is very hydrophobic. That's kind of the deal here. And because of that hydrophobicity, something like a negative ion is not going to be very happy to be interacting with the interior of the membrane. So if we look at what will happen is the chloride ion will need to cross into the membrane. Well, that would mean that all of the waters would have to be stripped from the spheres of hydration, and you would have to, in essence, resolvate the chloride ion with these nonpolar groups, and then the chloride ion would have to get across, shed itself of those interactions with these hydrophobic interior of the membrane, and then get new waters put on to the chloride ion. So that's what would happen. So the chloride ion would pick up the waters. Well, a very similar thing actually will happen with indole as well. Indole will have an easier time making it through the membrane, or at least into the membrane. And if there were a sufficient gradient so that there would be more indole on this side, say, of the membrane than this side, then there would be a strong entropic driving force that would help the indole cross, because it will want to go from high concentration to low concentration. You see, at high concentration, let's just draw a little membrane here. Let's say you have a bunch of molecules at high concentration on one side and just not nearly as many on the other side. Well, these in high concentration are going to be in a more ordered state because there's less room for them to move around. entropy will drive them from high concentration to low concentration, because now there'll be more places where they can distribute. So that's entropic, sort of favorable entropy. That's essentially how gradients work. Well, it turns out that as you go through this whole thing, um, same thing happens with chloride. It's just that the chloride ion is much harder to get into the membrane to begin with. So indole will work better going through. Chloride ion will have such a high activation energy. So if I were to think of transport kind of like a chemical reaction, um, the let's say this is inside the membrane and this is outside the membrane. This energy of activation is what the major barrier is. If I have a gradient so that I'm going from the inside to the outside, and so this is in, out. If I have a gradient, then this will be spontaneous, and there'll be this energy of activation that's here to get across. If I have a reverse gradient where I'm going against the gradient, then I'm going to switch my pen color, then it would look maybe more like this. If that, it would take energy to get up, extra energy. It would be exergonic going across. That would be if I had higher concentrations of the thing being transported on the outside than the inside. That's what the red shows. So what a transporter does, so if we have some kind of a channel or a transporter, a protein that does the transport, is it lowers the energy of activation. It lowers the energy of activation. So in that way, a transporter behaves like an enzyme. It lowers the energy of activation to make this process happen. In what ways is energy used to drive transport through a membrane? What are some examples of the energy used? Well, the main ones are, gradients, chemical energy like ATP, hydrolysis, and stuff like that. And in some cases, there are things like voltage gating and stuff. So there's I shouldn't say voltage gating. I should say electrochemical gradient. So there's an electronic component, and then I should say light energy. So like rhodopsin or something in your cells can absorb light, and that light can be used to drive transport. Okay. Now, along the lines of energy, as how do active transport and passive transport differ? Well, it turns out that I think that it may be just a matter of semantics or wording, but I hear a lot of times that people will say that active transport requires energy, whereas passive transport does not. Well, that's not an entirely true statement. You see, in order for any transport to go, it requires favorable energy. it requires that delta G is negative to be spontaneous. In the case of passive transport, delta G is already negative. So passive transport, delta G is negative, and that usually means you're moving down a gradient. So if there's a gradient, they move down the gradient, so they're rolling down the gradient, and that makes for passive transport, delta G is already negative. All transport requires favorable energy to occur, okay? It can't happen without the release of energy in order to occur. Now, in the case of active transport, the problem is if you look at just the thing being transported against a gradient, because that's usually what happens, active transport, you're forming a gradient, delta G is positive. So in order to get this to work, you need to couple the transport with another process that has a negative delta G, and then when you kind of add the two together, you have a net delta G between the two processes that overall is negative. So if this is forming a gradient, okay, then delta G, you need to couple it to something that can help energize that process, and linking it to that process will create an overall net delta G that is negative. Then that reaction will occur, that transport will occur. Now, this is where we use ATP hydrolysis, or a gradient would be two examples. So if you have ATP hydrolysis, that has a sufficient negative delta G that when coupled with the formation of the gradient, which has a positive delta G, it will have excessive energy that's released enough to make this whole thing have a negative delta G. In the case of linking it to a gradient, if there's a gradient that's already formed, and that gradient will then be able to roll from high concentration to low concentration, and you can match it up or link it in some way to the unfavorable formation of a gradient, you add the two things together, as long as delta G overall between the two reactions, between the two gradients moving, is negative overall, then you will form the new gradient, but you'll lose the other gradient. That energy will be transferred from one gradient into the other. So really, I have talked about this question here. What is the role of entropy in transport? Well, there's a couple of ways I could say that it's involved. The easy one is in gradients. When you move down a gradient, when you go from high concentration to low concentration, I'm just going to use the concentration steps. When you go from high to low concentration, you have a favorable entropy. Entropy increases. It becomes more disordered, and that is very favorable. The other part where entropy factors in is, say, in the case of ATP, okay, ATP hydrolysis leads you, I'm not sure why I just put a plus there, sorry. I meant to put a plus here. To two molecules, so you go from ATP to two molecules. Well, that is also favorable entropy because you're taking one molecule and distributing the energy into two molecules. And that then can help form a sufficiently negative delta G that it can help drive the transport process. So if you look at what cholesterol does, okay, it doesn't affect the melting temperature, the phase transition temperature, where you go from more fluid to more solid, and vice versa, depending on which direction you're looking at. The membranes are mobile, they move around, but they kind of can have more of a solid phase versus a liquid, more fluid phase. And so that temperature, right, known as the TM, that's sort of where the phase, if you will, the phase transition would take place. Well, cholesterol kind of dampens the effect of temperature. You can see that fluidity with response to temperature is not nearly as responsive when there's cholesterol already compared to this, which is very responsive where there's no cholesterol. So what that means is when you're above the TM, it makes the membrane less fluid, and when you're below the TM, it makes the membrane more fluid. It probably has a lot to do with the way that cholesterol, so if these are sort of your the one leaflet of your membrane where it has all these fatty acids, then you have your multi-ring cholesterol involved, intercalated, and it will kind of get in the way of packing, so it's a little more disordered in the fluid state, but it will also get in the way of movement because it's kind of blocking the way for when it's above that state, that transition temperature. So what does the data say? Oops, dang it. I have to check something. So what does the data say about the two forms of transport? Well, obviously that got this is the second part of that, so we're comparing the two transports between these two molecules, indole and glucose. Well, indole looks like it is just moving. There is a linear relationship between the rate of transport and transport. The concentration of indole. And it looks linear and it doesn't look like it ever saturates. That would be maybe consistent with the indole being able to pass through using passive, non-facilitated transport. So it would not be. It's just simple diffusion. Okay, so it'd be just simple diffusion. Whereas glucose saturates. Well, that indicates that there is a transporter involved. So there would be a transporter, and that would be facilitated diffusion. Facilitated. Now, this does not mean that it is active necessarily, because you could still have facilitated transport that's also passive. But it could be active if the transport formed a gradient and was coupled to another very favorable chemical reaction that helped drive the overall process. So if there was an issue with membrane fluidity, proteins are always moving around. In order for membranes to function properly, the proteins need to move around and be mobile. If they were too fluid, the proteins would move too much and potentially move away from each other and have a lot more less restricted movement, which could alter the function of the membrane if And if it were obviously too rigid, then you would have an issue with the proteins not being able to move as much, and proteins need to move in order to work. Why can addition of detergent dismantle a membrane? Well, detergents usually have some kind of a polar or charged group, and then an uncharged group. Well, these things can get into the membrane and potentially coat the inner leaflet with negative charges, and the outer leaflet of the membrane with negative charges or positive charges, and that could help essentially solubilize the interior of the membrane, so it would, so you would be able to add these negative charges, kind of like what SDS does with sodium dodecyl sulfate does with a protein. It can help solubilize the nonpolar parts so they make better connections with water. I mean, that's kind of how detergent works. So that could screw things up. This is really just an old-fashioned double reciprocal plot, because turns out you can treat, that's 1 over V, you can treat transporters like enzymes, and they follow Michaelis-Menten kinetics. So all that Michaelis-Menten stuff that you did applies here too. So if I had a situation like this, yield a straight line, I could treat it the same way, whereas this would imply, if this followed Michaelis-Menten kinetics, this would imply that it's facilitated, uses a protein to facilitate transport, and then Vmax is equal to 1 over 441, and I said that the rate is in nanomole per second, so that's nanomole per second, and I'll let you do the math, but flip that around and you'll get some number. I don't have my calculator handy right now, but that's how you set it up. And then once you have your Vmax, then you just multiply your Vmax that you get times the slope, because the slope, so whatever you get for Vmax, you multiply that by your slope, which is 6681. Because remember, slope is Km over Vmax, so your Vmax's would cancel out, leaving you with your Km. And then you'll get that number. And so I assume you can punch numbers on your calculator. You should be good to go.